Hey everybody, welcome aboard. It's time to look at an introduction to differential equations today. And actually, differential equations is something that you've kind of been exposed to already. You might recognize some of this work from your quiz and your homework last week, where we're given a velocity function 1 plus sine t with the initial condition s of 0 equaling -3. This is known as an initial value problem, where we're basically going to be asked to find the position function originally. So in order to move from velocity back to position, I'm going to go ahead and take the integrals of both sides. I get the position function here being, if I integrate this with respect to t, what I get is t, and then remember, the integral of sine is going to be negative cos, and I have to remember that plus c, that constant of integration that's always appearing there, accounts for some kind of vertical shift of sorts. And this would otherwise be our position function, except they gave us this initial condition here of s of 0 being -3. Well, what does that mean? It means that if I plug in a 0 for t, in other words, if I get 0 minus cos of 0 plus c, I will actually get a -3 as the answer. And so 0, well, that obviously goes away. Cosine of 0 is 1, so this negative on the outside makes it -1 plus c, and that equals the -3, so c is equal to -2. And so how does that help me? Well, it helps me because now this function can be considered s of t being a complete and, otherwise fully completed position function. So what we get is t minus cos t minus 2. Not plus c anymore, but rather minus 2. And that is the formula for the position that passes through this point. So relatively doable stuff. That's what's known as an initial value problem. Now, what we're going to do is we're going to work on a couple of initial value problems, and just to get ourselves warmed up. So I'll go ahead and write one down for us. Give me a second. So here's the first of our examples. It's dy dt equaling secant squared t minus sine t with the initial condition of y of pi over 4 equaling 1. So again, the first thing I'm going to do, and this is actually really important in regards to the AP exam, is I'm going to go ahead and separate the terms. And what I mean by that is I'm going to get all my t things on one side. So I have dy equaling secant squared t minus sine t dt. And now from here, I'm going to go and integrate both sides. Now, this expression right here should look pretty familiar. We've seen this many, many times before. If I integrate dy, I get y, and that's going to equal, well, what's the integral of secant squared? Well, that's going to be tangent of t minus the integral of sine is actually going to be negative cosine, so this is actually not minus at all. It's going to be plus cosine of t plus c. Now again, I'm going to solve for this plus c, just like in the last problem with the velocity and the position. So I know that if I plug in a pi over 4 for these, so if I get tangent of pi over 4 plus cosine of pi over 4 plus c, I will get 1 as my y value. See, y of pi over 4 gives me 1. Plug in a pi over 4, get out a 1. Very cool. So tangent of pi over 4, a little bit of unit circle, 1. Plus cosine of pi over 4. I'm going to go and call this rad 2 over 2. I don't know why, but I think that might help me. Actually, no, it won't. Minus 1 from both sides. We all know what happens there. 0 is equal to rad 2 over 2 plus c. And it's no secret that c is going to equal negative rad 2 over 2. So again, how does this help? Well, it means that the original function here that passes through the point 0, 1 is going to be tangent of t plus cosine of t, not plus c anymore, but rather minus 1 over rad 2. I'll put him in there this time. That way he doesn't feel left out. Okay, so that's initial value. And basically a differential equation is going to be very, very similar. So let me go ahead and upload one. So here we are at differential equations. Now, you guys actually know the fundamental basis of a differential equation because we've solved a couple of them before in the velocity versus position function and then what we just saw earlier. So I guess the fundamental definition of a differential equation is one that involves the derivative of an unknown function. So, let's take a look at our first example. The only thing we're doing is we're really ramping up the algebra going on here. And when we first do a differential equation, we want to definitely separate those terms. Get those terms to each side. So I want to move all my y's to one side and all my x's to the others. How do I do that? Well, I'm going to go ahead and divide by y on both sides. So I'm going to divide by y, multiply by y here, and I'm going to go ahead and move the dx over. So what I get is 1 over y dy is equal to negative 3 dx. Once you get the terms separated, and this is really, really important, if you do not separate the terms, there are AP rubrics out there that say that you get a maximum 3 out of the 9 points. So separating the terms is super, super crucial. So now that we're set up in this position, I am going to go ahead and integrate both sides. Now, how do I know that I can do that safely? Well, it's because all my terms are separated. So once my terms are separated, I go ahead and integrate. Now from here, things can get a little bit dicey. The integral of 1 over y dy is not y to the 0 over 0. It's not that it's undefined. It's that we get the natural log of the absolute value of y plus, I'm going to call this c1. In other words, it's the first constant. We always remember that plus c, right? And that's going to equal, well, the antiderivative of negative 3 is going to be negative 3x plus c2, the second constant in this. And now from here, I'm going to go and subtract c1 from both sides. And so what I get is I get the natural log of the absolute value of y equaling negative 3x. Now you guys are going to love this. c2 minus c1 is actually c3, the third constant, whatever constant that is. A constant minus a constant is a constant. I just don't know what that constant is. We will eventually, later on today, find tools that allow us to figure that out. But right now, let's just take it one step at a time. From here, I'm a little bit stuck, and it's hard to see exactly what you're supposed to be doing here. But if you remember back to Algebra 3-4, if I have the natural log, or any kind of log, of something equaling some kind of deal on this right side here, I can go ahead and change forms. I can say that e, which is the base of natural log, raised to the 3x plus c3, and that's going to equal the absolute value of y. Hope we're doing okay so far. From here, I'm going to go and split them back up. So I'm going to go ahead and go y, absolute value of y is equal to e to the negative 3x. Now check this out. What I have going on right here is I have two terms that are being added together under the same base. Now I'm going to go ahead and use a little bit of reverse exponential rules here and say that if I have two terms in the exponent being added, that means that the bases were actually being multiplied. So hopefully you guys are able to figure that out. And now from here, you guys are going to love this. E to the c3, some constant, right, raised to some constant. You'll never guess what this is. E to the c3 is c4. And that's going to be multiplied by e to the negative 3x. And I have the absolute value of y equaling that. And now we're almost there. Once we're done, notice how I've got this absolute value of y here. Well, with this absolute value of y, technically, what I have here is plus or minus c4, right? Because absolute value can be positive or negative on the inside if I was to split up the absolute value. And so I'm going to go ahead and say, well, plus minus c4, well, that's pretty easy. That equals c5, the fifth constant in this whole thing. So I get y equaling c5 e to the negative 3x. And that is the solution to your differential equation right there. Now, the hardest things to keep note of is the split between this step here to this step here. So I hope you guys are able to do that. Let me reiterate that one more time. I've got two things in the exponential area being added together, which means I had to have been doing something with two different bases. Those bases were being multiplied, because if they weren't, then these things couldn't be added. It's almost like if I had a to the 7th times a to the 4th, I get a to the 11th. So that's because I have a to the 7 plus 4. I'm just working that rule backwards. All right, so hopefully that makes it a little more clear. Let's get another example going on. And here we are again, another differential equation. So again, before doing anything, I'm going to go ahead and separate those terms. Get all my y's to one side, move all my x's to the other. So what I've got is y squared dy is equal to 2x dx. Again, once I've got all my terms separated out, now I'm going to go ahead and do this integration here. So let's be careful here. The integral of y squared is going to be y cubed divided by 3 plus c1, and that's going to equal, well, what's the integral of 2x? Well, that's x squared, right? X squared plus c2. So now from here, this one's a relatively straightforward kind of problem here, where I end up with y cubed over 3 is equal to x squared plus c3. And then from here, I'm going to go and multiply. Wow, that was not good. Multiply, better, by 3. Again, at this point, I'm just getting y by itself. So y cubed is equal to 3 parentheses x squared plus c3. And then from here, I end up just cube rooting both sides. And I end up with y equals cube root of 3 parentheses x squared plus c3. And that's it. Very cool. Let's try another one. Okay, so you knew this was coming. Trig one is inevitable. And so I'm going to go ahead and move this guy over. So I've got dy is equal to tan x dx. Now, at some point, you might, after you do about 50 or 60,000 of these, you start to kind of have an intuition as to what tan x is going to be. And of course, it's probably going to show up as a multiple choice, so you probably don't want to waste too much time on this. But let's just see where this comes from. And so if I integrate both sides here, well, I got a little bit of a problem here, because I'm not really sure exactly what the integral of tan is. So let's go ahead and find out exactly what tangent is. Well, tangent is sine x over cos x dx, right? And so if I integrated that, I could use an old friend called this. Good old u sub. So what we've got is I've got, if u is equal to cos x, then I know that du is equal to negative sine x dx. You see how I saw the function and then I saw its derivative? In other words, this negative will jump over here so that I get negative du is equal to, sine x dx. Now from here, that's what this guy can become. So what I've got is the integral of 1 over u du with a negative on the outside. And that's y equals, right? Because I've already integrated the y side. So what do I get? Well, what we get is we get y equaling negative ln of u plus c. Well, what was u the entire time? Well, that's cosine. So y is equal to the negative natural log of cosine of x plus c. Now, you could leave it like that. What you find, though, is that some books and your answers on the AP exam will most likely kick it in and call it y equals natural log of the absolute value of secant plus c. And eventually, after you do, like I said, about 50 or 60,000, you kind of commit it to memory and it just kind of becomes there. So anyway, hopefully that makes a little bit of sense to you. And for the grand finale, let's go ahead and combine some of these skills together. And for the grand finale, let's go ahead and combine some of these special skills that we've learned over our long career together. So I've got dy dx equaling negative xy with the initial condition y of 0 is equal to 5. So it's an initial value problem involving a differential equation. Obviously, like putting ice cream in the freezer, we are going to separate those terms. So I got 1 over y dy is equal to negative x dx. So let's integrate. I've got natural log of the absolute value of y plus c1 is equal to negative x squared over 2 plus c2. Now at this point you can actually kind of diverge on the problem. You can solve for c here if you wanted to, or you could wait to the very end. Normally I wait to the very end. I'm trying to think there might be some merit to solving in the beginning. I can't really think of an example off the top of my head, so we'll just go ahead and proceed forward as if we are going to solve for c at the end, because that's exactly what we are about to do. So natural log of the absolute value of y is equal to negative x squared over 2 plus, again, c2 minus c1, that's c3, right? Again, the second constant minus the first constant will give you the third constant. From here, I'm stuck. Natural log of absolute value of y is equal to this nonsense. How do I operate this? Well, I got to go back to those log rules. And I'm going to go and change forms. E to the negative x squared over 2 plus c3 is equal to the absolute value of y. Now again, I'm going to go ahead and do exactly what we did 2 examples ago. Absolute value of y is equal to, now if I look at this expression right here, they both have the same base, right? Otherwise, I wouldn't be able to add the exponents. So these exponents are having the same base here. So I've got e to the negative x squared over 2 times e to the c3. Now, what is c3? E to the c3? Well, that's simple. It's c4. In other words, e to the third constant will get you some kind of fourth constant, and I got e to the negative x squared over 2. And again, that's the absolute value of y. So, well, what's the absolute value of y equaling all this? Well, if the absolute value of y is equal to plus or minus c4, that means that I would end up with the fifth constant if I was to call it that, right? So the fifth constant, would show up if I was to actually apply that absolute value. Now from here, I'm not done yet. I gotta still solve for c. Remember this guy here. Don't forget about him. We have not even messed with this guy yet. So let's go ahead and mess with him now. I know that if I plug in a 0 for x, not for c, right? I'm solving for c. If I plug in a 0 for x, what do I get? Well, I get e to the 0, right, times c5 is equal to 5, right? Because if I plug in a 0, I get a 5. Well, e to the 0 is 1, and 1 times c to the c5 is c5. So c5 equals 5. So what I have here is y equals 5e to the negative x squared over 2. Okay? And that's differential equations for you, at least at this level. So hopefully this is informative. I will be back in the next video with some homework questions from last night. See ya.